Okay, so let me say a couple things about the next homework. So the first one, I think is kind of a cool little problem. Let P and Q be projective R modules. Show that if you tensor P and Q, it's again a projective R module. And I might give you that is what's my favorite characterization, what it means to be projective. The next problem, you're going to need this. I don't want you to prove it because frankly, I don't want to grade it. It's not terribly difficult, but it's just kind of grungy a little bit. So if you have an R module N, you can let the set S inverse N. So it's sort of like a localization, if you will. Think of this as fractions in the form N over S, where N is in the module and S is in the multiplicatively closed set. And we declare that two of these fractions, N1 over S1 and N2 over S2, are the same if and only if there's some T in S such that T times S2N1 minus S1N2 equals 0. This is quite familiar if you've been in localization range before. This is an R module with addition given by, you add the fractions, I think just the same way you think you would, and you multiply by a scalar the same way you did. So we're going to use this for this following magical mystery tour problem that I've affectionately titled Localizations Flat. So if R is an integral domain, N an R module, and S a multiplicative set as per above, show that every element of R localized at S tensored over R with the module N can be written as a single tensor of the form 1 over S tensor N, where S is an S and N is an N. So when you tensor a localization with your module, you can write things in this very kind of special form. It's very convenient. Show that there is an isomorphism, R localized at S tensored with N and S inverse N as defined above. This is a good practice, I think, of doing the kind of induce homomorphism from R modules. Show that a tensor of the form 1 over S tensor N is 0 if and only if there exists a T in S such that kills N. Tn is 0. And put this all together and show that R localized at S is in fact a flat R module. So this is a good way to build these flat modules that we talked about using this. And then finally, to kind of finish this off, show that Q, wow, that was a trick. Show that Q is a flat Z module, which follows from what the work you've done is, that is not projective. So that gives you a good example of something that's flat but not projective. Number 3. This is right. This is sort of this sort of thing that I remember topology. This topology person that I used to know used to say, tensoring with Q kills torsion. Right. So when you tensor with Q, in fact, just consider abelian groups. Suppose you take an abelian group you want and tensor with Q. See what happens to the torsion elements. This kind of illustrates this. Let R be an integral domain, quotient field K and M and R module. Let T of M be the set of X and M such that Rx equals 0 for some non-zero R and R. We actually talked about this last time. T of M is what I'm calling my torsion elements of the module. We have shown that Tm is a submodule of M. Show that M modulo Tm, so M modulo this, is in fact torsion free, right? So when you sort of kill all the torsion elements, you get something that is torsion free. And torsion free means the only element that has torsion is the 0 element, right? The only element that's killed by something non-zero is the 0 element. And this is what I mean by tension kills torsion. If you take your original module, which may be full of all kinds of torsion elements, and you tensor it with the quotient field, it's the same thing as tensoring this part with the quotient field in a certain sense. So basically, when you tensor with K, it comes through and it kills all your torsion elements, loosely speaking. Finally, 4, I promised you this one. This is the adjoint associativity problem. show, you can assume that R is commutative with identity, and A, B, and C are R modules. Then there's an R module homomorphism, R module isomorphism between here and here. We discussed what this one should be. See if you can figure out this one and then show that they compose in both directions to the identity. I think it's the best way to think the problem. Okay. Any questions?
You say that R being integral domain with quotient field K. Is that quotient field just all quotients of elements in R?
Yeah, that's
Like,
right.
like you defined up in the red.
That's exactly right. So another way to think of the quotient field for an integral domain is you're localizing it to a set of all non-zero elements. So you're allowing everything that's not zero to be a denominator for certain sense.
So would we write arbitrary elements in the same notation in the red up above?
Well, let's see. Yeah, sure. Yeah. Okay, other questions? Regular world. There we go. Okay, so let's kind of pick up where we left off. I got through parts A through D on our last theorem, and if you'll forgive me, I'll see if you guys can prove E, and if you can't, then give me a holler. I'm happy to help you out. So let's get this next theorem here as we're moving down the road, looking at the structure of finitely generated modules over a PID. Let F be a free module. Over a PID. If is a submodule then M is free and rank M is less than or equal to rank F. So now let me say a couple of words about this. I am not going to prove this in general. I suspect that you have probably seen this in one form or the other in the special case that F is a finitely generated free module. Well, you probably saw this last semester when you looked at the classification of finitely generated fitting groups. If this is finitely generated, the proof's not so bad. This actually persists to any rank over a PID, right? It can be countably infinite or larger than that even. This still holds. Rank, what I mean by the rank is the size of the basis, right? Because that's really the only item of data you need for a free module is you need to know the rank. So this is kind of a powerful theorem. If you're a module over a PID, then if you have a submodule, it is also free and has rank less than or equal to the rank free module itself. Like I said, and you actually need the axiom of choice to do this in general. For the finite case, you can use other techniques, but for this, you need well ordering. What you do is you take the free module. It's a direct sum of some number of copies of R that over some index set. You have to well order the index set and do some yin yang, and I don't really want to fool with this here. Let me give you an example. So let me give you an example. If you look at, let's look first at R equals Z6. Well, this isn't a PID. In fact, it's not even an integral domain, right? But I use this This is a free module. Rank 1 over itself. Right. However, R has submodules isomorphic to Z mod 2 and Z mod 3. And of course, neither of these can be free Z6 modules because they just don't have enough elements. All right. Because well, they're clearly non-zero, so it can't be a zero module. And any free module that's not zero and finitely generated, the number of elements in it has to be a power of 6, which neither of these satisfy. Let me give you one more non-example. You might think that the previous one was a bit of a cheat, but maybe it is because of the fact it's not domain. Did you all ever look at this ring? And this is a common ring to look at in Algebra 1. Maybe when Matt was talking about things like factorization or things like this. Well, and in fact, it's exactly this bad factorization that allows me to do this. A free R module of itself. Right. So just take the real itself. Now consider let I be the ideal generated by 2 and 1 plus square root negative 5. I'm not going to go through the details of this because we're actually going to get to this later at this point, of course, but you can hear me now and believe me later. This ideal is not strictly contained in R, so there's no linear combination of this 1. And right, so this is a proper ideal and it's 2 generated, right? But this is not free. Because you can prove that if this is free, you need a basis of 1 element. And this can't be generated by a single element. Right? And in fact, you can play around. You remember how Matt did the bad factorization? Perhaps 6 is 2 times 3, and it's also 1 plus radical negative. This time it's conjugate, right? You can actually use that to show that this set is actually linearly dependent. So, by the way, it is interesting to notice that this is, in fact, it's not free, but it is, in fact, projected. But we'll talk about that later. Okay. So the big takeaway, though, is this theorem here that if you have any free R module over a PID, right, and that's what non-example 2 shows, because this isn't, it's not a UFD, so it's not a PID. Then any submodule is free and rank is no more than the rank of the parent module. So corollary. (713) let R be the PID and an n-generated R module. So finitely generated, say by n elements, then any submodule of A can generate it by any submodule can be generated by no more than n elements. Okay. And let me give you another corollary, then we'll discuss this. Corollary. Corollary 714. Let me be a module over then the P is free if only protected. Okay, so this is another good observation. This observation is actually kind of interesting computational one. And this one is sort of interesting because what this shows you is if you look at modules over PID, modules over a field, vector space, all modules are free. If you look at modules over PID, then the notions of free and projective are equivalent, right? So at least every projective module is free, right? So let's look at this. I like this one because it says, okay, I've got a module over PID and I have a submodule. Then I can generate it by I could generate this by m elements where m is less than or equal to n. Right. This is really kind of a cool result. I mean, this seems sort of intuitive, but if you go back to that non-example 2 I did, right, with that ring z adjoined with square root -5, notice as a module that's generated by 1, it's got a submodule that requires 2 generators, right? Over PID, this can't happen. If you've got a submodule, it will have less generators. So how are we going to prove that? Well, let's let A be our n generated R module. And B in A submodule. Right. So how are we going to bootstrap this thing? This says something about free modules. Yes.
If free module announced on the 8. So
Okay. And in fact, I know I can do a free module break in exactly, right? So okay. A is homomorphic image of correct. So there is a map from here to here. that is onto. How does this help us with our B? Well, notice that we have a B. Right. So, any ideas how we can use this?
You can sort of take like a pre-image.
There you go. Consider. Well, let me call this, just so I don't have to write a direct sum every time. Let me call this F3. This is the set of X in F such that P of X is in B. Right? This is a submodule of F, and so P n plus B is free by our illustrious theorem here. Right? Note that so P inverse B is generated by less than or equal to n elements. Again, by theorem 712. Hence, so is B as B is homomorphic image. Of the inverse. And any homomorphic image of any module is generated by the cosets that correspond to the generating set. And some of those cosets may collapse at the same thing, so we get the inequality we want. Everybody okay? Now, how about 714? Let's take a quick glance at that. Well, we know free implies protective. No problem there. I mean, that's a universal truth. For ours, we need to show the projection implies free. Well, what does it mean for P to be projective?
It's a direct sum.
Yes, you've got your finger on the pulse of my favorite one. That's right. It's the direct summing of a free one. Then there exists K such that P sum K free. But P is a submodule of this free. So P is free. Because that's what we said in theorem 712. Okay, any questions? Okay, so here's one that will be actually kind of important in the structure theorem when we put it together. Oh, by the way, let me tell you folks, before I end class and then forget this, I need to go watch somebody. I need to do a teaching observation today. I need to leave my office at 11 o'clock. If you're planning to come see me, just come give me a whisper after class and I'll set up something later, probably in the early afternoon if you like, or we'll arrange something. And also probably over the course of the next week, I'm probably gonna have to do things like this periodically. I'll let you know when I have to be out because we've got candidates coming in for a job search that I need to be at. But If you have to miss me, I promise I'll make it up to you. Okay, theorem, any finitely generated origin free module over a PID is brand. So if you have a module over a PID and it is finally generated and it's got no torsion, it's guaranteed to be free. Now, before I prove this, and actually this should be a hint because I'm willing to bet that when I do my proof, you're going to see somewhere where I'm going to use finite generated, somewhere I use torsion free. Both of these are necessary. Example. Both these examples are over Z. Notice that Q is torsion free. But not free. It's not finitely generated. I'm not going to show the details of that because actually in your next homework, you have to show in fact, not only is Q not free, it's not projected, right? Of course, that's equivalent. Free and projected are equivalent. Because Z is a PID, actually. Right. And two, Z mod N is finitely generated. Well, here we make sure that N is bigger than one. It's finitely generated, but not free. It's not for you. Yeah, certainly. I think the fact that Z mod N is not free is a little bit clearer because if you take any single element Z mod N and you multiply it by 6, you get 0, which means that there are no singleton elements in Z mod N that are linearly independent. So this has no chance of having a basis. Right. So both of these assumptions seem quite necessary. So let's see why this is true. Let A be our module. And we'll say A is generated by X1, X2, Xn, and is torsion free. Let me just remind you so that we're all on the same page. What I mean, I'll write up here. What I mean by torsion free is if you have a non-zero element, say A, that lives in A, then RA equals 0 implies R equals 0. Right. So torsion free means the only element that can be multiplied by a non-zero element gets 0 is 0 itself. Since A is torsion free, E Xi singleton set is linearly independent. Now, we're going to have to do a little bit of a little bit of strange yin yang here, right? Because what you're used to, I guess, in linear algebra is, you can start with any linearly independent set and expand it to a basis, right? You can't always do that. We've seen examples of this even for free modules over Z, right? 2 by itself is a linearly independent set, but it doesn't expand to a basis Z. So I'm gonna have to be a little bit careful here, but I do know that each single xi is a linearly independent set. And so we find x1, x2, xk a maximal linearly independent subset. With perhaps reordering on my initial numbering if I have to, but without loss of parallel, we find this thing. So this, and maybe this is just a singleton, right? But I find the maximal linearly independent subset that I can. So let me point out, if F is equal to the submodule generated by then F is free. Right. So if I look at just what's generated by that maximal linearly independent set, that has to be this has to be a free module because this in fact forms a basis, right? Because it's a linearly independent set, and by definition, this spans F. So here I've got this free submodule of A. Let me make the silly notion that if F equals A, then done. Because that was our goal, is to show that this thing actually has to be free. If not, then we're going to do the following bit here. So we suppose that we have that x j is not in F, or let's look at the K. We suppose that here. No, for each such J, there is RJ and R such that RJ XJ let me make sure I get my indices right here. RJ XJ is the sum. Right. Right. So what are we saying here? What we have is we have these elements, they're a basis for the free submodule. And we notice that if you have any xj that's beyond those bounds here, that is k on the end, I can find an rj such that in R, such that this is pushed into here. Can somebody explain how I know that we can do that? This is because the set xk and then xj is linearly dependent. Right. And so in particular, rj is not zero. Right, because if this were zero, this would force the rest of these to be zero. Right, okay. So what I'm going to do is I'm going to collect all these non-zero RJs for j going to k plus 1 up to n. And I'm going to do this. Let R so for every j between k plus 1 and n, I find one of these RJs. Take them all and multiply them, they're all non-zero. And I get that this, of course, is not zero because R is an integral domain and all these RJs are. And let me point out that now notice what we're saying is for every xi, the original generators of the basis element, then Rxi is in F. This is no problem if the indexes are up to K, right? I agree with that, because if the index is up to K, then each xi is already in F by itself, right? But if, for example, you have K plus 1, notice that Rk plus 1 times xk plus 1 is in F, right? And this R has Rk plus 1 as a factor, right? Right, okay. So each of these, R contains each of these little RJs, and each RJ knocks the appropriate thing into F. So in particular, this particular R times every one of the generators, X1 up to Xn, lands you in F. So it should land every linear combination of those in there. So in particular, RA, everybody okay with that? So now we've totally got it. So this gives us a homomorphism. I will call it P, A, and F. Given this way, given by phi of A is RA, right? And I know that this is good because R times anything in A lands you in F, so this has the appropriate codomain. Let me point out that B is an R module homomorphism. That's easy to verify if this multiplication by a fixed R is an R module homomorphism. And phi is 1 to 1. Because if A is in the kernel of phi, then phi of A of RA is equal to 0. Which implies that A equals 0 as A is torsion free. Okay. Therefore, A is isomorphic to a submodule. Well, isomorphic to phi of A, which is a submodule of F. So phi of A, hence A, is free. Right, okay. Okay, let me make a couple of remarks. First of all, there's the torsion free assumption. And there's your finitely generated assumption, right? Because if you had infinitely many generators that you needed to do this to, there's no way you can do this trick anymore, right? So it's funny because in two reasonably subtle places in the proof it comes up, these assumptions are needed, and they are crucial by our two non-examples that we gave before this. Okay, any questions? Okay, so let me give you a corollary to this. And this is the first big part of the structure. Corollary. Someone wants something 5 or 6. 6. Let A be finitely generated. Module over a PID. Then F is I'm sorry, A is isomorphic to F directs A is where F is free or finite rather. AT is torsion and F is isomorphic to A mod AT. Okay. So this is kind of the first big piece. Remember, probably, and this very much mimics what you all did probably with finitely generated abelian groups. The theorem for finitely generated abelian groups is if you have a finitely generated abelian group, it's got a free part, it's got a torsion part, right? And the free part is completely determined by its rank. You know how many direct sums of Z you have here. And this you wrote in terms of elementary divisors or invariant factors, or whatever you have to do. Let me give a quick proof of this anyway. let AT be the set of A and A such that RA equals 0 for some non-zero R. So this is the torsion element. I think I call this T of A in the homework. This is a set of torsion things. We've shown, again, we've shown that this thing is a submodule. You don't really need this you don't need PID for this to be a submodule, but you do need integral domain. Right. So consider the inclusion function from A to AT, right? So the torsion module is a submodule, so this is just 1-to-1. This is a short exact sequence. And this is projection. A goes to the coset A plus AT, correct? So let me make a couple of observations. If you're used to quotienting out by things, when you take a module quotient out by its torsion elements, you should get something with no torsion intuitively. I'm not going to prove this because it's actually a homework exercise. You actually prove this in the upcoming homework, but this is torsion free, right? So if you give me that latitude there and finitely generate it, because A is finitely generated. This is an onto map. This is finitely generated, so its image is generated by the cosets of the generators here, and so it only requires finite image. Okay. So A mod AT is finitely generated and torsion free. So improved. But because it's also free implies projected. So sequence splits. Right? And since the sequence splits, we get A, it's isomorphic to the ends, which is AT, direct sum A mod AT, and here's your free part. So there, I like that little corollary because it uses a lot of the tools we have and it brings it together in short order. Okay, any questions on that? Okay. So we've got two more things to do before I can give you the whole structure there. Let me just give you one of them now. Theorem 717. Let A be a torsion module. So to understand this decomposition now, all we need to do is understand the rank of this, which is finite, and we need to understand what the torsion piece looks like, right? How can we write the torsion piece? Well, here's the first key that we have to do this. So let A be a torsion module over PIDR. And let P be a non-zero prime. And A sub P is going to be the set of A such that A is killed by a power of P of some K. So this is a torsion module, so it's killed by some elements of R. Let's collect the ones that are killed by a power of this prime P. Then A in other words, A is generated by all these P torsion models. And if A is finitely generated, then AP equals 0 almost everywhere. And remember, what I mean by almost everywhere is all but for finitely many. So if it's a finitely generated module, there's only finitely many primes that you have to use. Okay, any questions on that? Any questions? All right, well, y'all have a good one, and think about coming to the math club. It should be a fun one. Stay